Hello, this is a presentation of the paper 3D Local Planning for Forestry UGV based on terrain gradient and mechanical effort. Forestry navigation is still a not very explored subject, having many challenges, like the illumination, vegetation characteristics, the rough terrain condition and slippage make the odometry not reliable, the unstructured environment make it difficult to perceive and localize, and the forestry vehicles are typical large heavy-duty machines, make the process a hard task due to safety concerns. In addition to this, forestry vehicles are very useful to forestry cleaning, for example to prevent wildfires, which motivates the Safe Fire project in which this work is inserted. There are already some successful works that can represent and navigate in forest environments. Because in this work we make use of ROS, few examples of ROS package include the navigation mesh and the traversability estimation. This package can represent the environment in a 3D elevation map to use in navigation. Others represent the cost of traversing a cell in a 2D grid. But most of them don't take into account the power consumption of the robots and our definition of mechanical effort, the amount of additional burden of a UGV when climbing hills in rough terrain environments. We have developed an algorithm that uses information from the robot sensors to create a 2D map that takes into account the mechanical effort of the robot. This map will be used as the cost map for the path planning of the robots. In this work, we only take into account the local path planning. The global path planning was not our concern. The mechanical effort calculation is the main contribution of our work, and how it was discussed in the previous slide, we have developed an algorithm that uses 3D point clouds from the robot sensors to estimate the cost of traversing each individual cell in a grid, producing a cost map for the navigation. This node is divided in three main blocks: the ROS interface, where we subscribe to the sensor data, the 2D projection and interpolation, where we project the 3D data from sensors in a 2D grid, and the third block, the gradient and effort calculation, where we calculate the gradient and the effort of each cell of the grid. First block, the ROS interface, will subscribe to the leader point clouds and convert these 3D point clouds on X, Y, and Z coordinates. These points are transformed from their respective frame to the robot base frame and concatenated in a single matrix, where each line represents a point of the leader and each column represents the X, Y, and Z coordinates of each point. This matrix is sent to the next block, the 2D projection interpolation, where this block is divided in three main blocks. In this diagram, we can see the three main steps of the 2D projection interpolation. In the first step, we will do a 2D projection of the LiDAR points in a 2D grid, representing each point as the equation. The X and Y are the index of the cell and the Z the information. Because each cell is a distance range, some cells can have more than one LiDAR point, and for the cells with more than one corresponding point, we take the median of the Z values. In the end, this results in a plot similar to the one we can see to the right. In this graphic, we can see that this process results in many empty cells, being necessary interpolation to obtain the estimation of the value, what takes us to the second and third steps of this block. Like it was discussed in the previous slide, in these two steps, we will estimate the value of the cells without information, with the adaptation of the nearest neighbor interpolation. In this adaptation, we analyze the lines, the columns, and the diagonals to find neighbors with information and compute the median of them. But before that, the strong discontinuities are filtered with the next equation, where the Zi is the Z value of the certain neighbor, the Z average is the weight average of all the neighbors, and the rho, the threshold that was empirically chosen. Only the neighbors of a certain cell that fulfill this condition are treated with the median. After applying this interpolation process, we obtain the result seen in the plot on the right. So here's the before and the after, where we can see that after the interpolation, the map is now complete enough to use for our purposes. The 2D grid that comes from the second block is used by the third block to calculate the gradient and the effort. In this block, we start by calculating the gradient in each cell, representing them by the gradient in x direction and the gradient in y direction. This results in the right plot, where you can see the gradient arrows. All the cells with gradient norm above a certain threshold that was empirically chosen were automatically considered as an obstacle. The rest of the cells were treated with the product between the gradient norm and the effort. The effort is used to distinguish upward from downward slopes and is defined as the cosine of theta. Theta is a relation between the vector that connects the position of the robot with the position of the cell we are analyzing and the gradient vector in that cell. In the end, if the effort is above zero, we are facing an upward slope. If effort is equal to zero, we are on a flat terrain, and if effort is lower than zero, we are facing a downward slope. This is an example of a resulting local cost map of the robot, which varies from white to black with all ranges of gray. White means we are facing a downward slope with a gradient norm equal to the threshold, and black facing an upward slope with a gradient norm equal to the threshold or an obstacle. To send this map to the mu base, it is needed to do a normalization of the values, because the occupancy grid map works on a range of probabilities that range from 0 to 1. In this paper, we will test and compare the applicability of some local planning algorithms to see if they take into account the mechanical effort of the robots. The algorithms we will test are the Bayes Local Planner and the DWA Local Planner. The tests were made in a simulated environment created with Unity that are shown in the right picture. To test the approaches, we will use three different scenarios. A first one, a simple planner scenario with some obstacles. A second one, a forestry scenario with small elevations. And a third one with large hills and big elevations. To test and compare the existing techniques, we use the following metrics. The elapsed time, that is the total time from initial pose to the goal. The traveled distance, that is the Euclidean distance between the current and the previous position measured every 0.1 seconds. The total cost, given by this equation, is obtained with the sum of all values of the gradient z, and the upward cost, given by the second equation, is obtained with the sum of all positive values of the gradient z. This means only the upward slopes. In this first scenario, we can conclude three things. Existing techniques make efficient use of mobility resources. They can go from initial to a goal point efficiently. Both algorithms choose the shortest path, having a travel distance very similar. And being a planar scenario, it is expected that the upward and total cost be about zero, with a small variance. In the table, we can see that DWA have a negative total cost. This means that the z-value went down more than it went up, but in this case it's not significant. With these results and the results of last scenario, we can conclude that DWA is slower than Bayes Local Planner, taking more time to reach the goal. We also can conclude that DWA choose a slightly shorter path with a slightly higher cost. But in general, the difference is not significant. Both of them tend to choose to go over the elevation and not deviate them. In the third scenario, we can see that the difference of the upward cost was bigger. The DWA tended to go more uphill than the Bayes Local Planner, as it can be seen in the graphics. But in these graphics also can be seen that both of them prefer to go up and down the hill instead of circumventing it. So, despite the fact that the base local planner have a better report cost, both of them don't take the mechanical effort into account as they could. After the result, we can conclude several things, like, in general, both algorithms do not take into account our definition of mechanical effort. So, this can be redefined to produce more economical trajectories, avoiding slopes, and preventing the robot to just choose the shortest path, like we intend with our method. So, in the future, we'll intend to compare our approach with the standard techniques and prove that our approach takes into account the mechanical effort and the power consumption of the robot. And when a stable approach is proposed, the test will be transferred to the real robot. Thank you for your attention. Feel free to forward us any question.